So, good evening, everyone. It's my third or fourth lecture, depending on how you count. Okay, so today we'll continue our discussion on Module 4, but then we'll also start transitioning to Module 2, and then we'll also start transitioning to Module 4. I know that some of these topics are being covered by the other instructor, Dr. Singh from ISM. Okay, everybody can still hear me, right? Okay, great. So there'll be some overlap in the topics that she will cover and I would cover. So I'll try to make sure that the overlap is minimal. Okay. All right. So this is just like a visual of where we are. So like I said, Module 2 and 4. So we were talking about more or less identifying stakeholders and their preferences, and we said there was two different ways we can think about people's preferences. One is that their preferences from an individual product, and that helps with the design, and also preferences in terms of whether the manufacturer or the company that manufactures the product would be able to sell in the market. So then you start thinking more demand modeling and things like that. So we'll continue in that vein for a little bit, and then we'll go back to our concept generation, concept evaluation discussions that we've been having. So here's the overview of my talk today. We'll continue our discussion on needs assessment, demand modeling, and product diffusion. And then concept generation, followed by brainstorming, creativity, design axioms, and then the chemical scrubber example, concept evaluation and selection, and then building models, right? So just like basically why all this discussion that we've been having forces us to build mathematical models that can help us predict things, help us make decisions, right? So obviously we won't cover everything today. We will foray into design optimization and multi-attribute decision analysis to do this a little bit more formally. And if you want to talk about models using software approaches, then Dr. Singh has been covering that from my understanding. So we talked about alternative marketing strategies. We don't have to go over this again. We talked about the leasing models, razor and blade models of product marketing, where customer is basically buys a product and then is now forced somewhat to buy repeat purchases of something that goes with the product, right? So printers and cartridges, you buy the printer, now you're forced to buy the same cartridge over and over again, similar and so forth. And then the other attribute we touched upon last time was time, right? Of course, you think that you can sell something. You think that people are interested in something. You think people want something, right? No way you're going to convince me that people's preferences don't change over time, right? People's preferences change. What was acceptable today is no longer acceptable tomorrow. In fact, I don't know if you watch movies from 20 years ago. They have cell phones. I'm like, whoa, who would use something like that? Well, that was state of the art then, right? So those kinds of things happen. So time is a big element, right? And time is a big element, not just because the preferences change, but also how your product diffuses through the market. It's not like you have something to sell and everything sells on day one and you're done. That's not how it happens. Like people over time will purchase it. When Apple releases their new iPhone in October, let's say, it's not like they sell everything in October. You could see that people start buying it, and then over time, more and more people buy it, and then it diffuses into the market, and then over a year or 2 years, then the sales drop, and then eventually they will launch a new version of it, right? So time is a big element, both in terms of how people's preferences change, but also in terms of how your products diffuse through the market. So one common model that you might have heard of or might not have heard of is the Bass diffusion model. Here's a basic differential equation that you would see for this. Of course, all these topics are supposed to be to, number one, point out what all there is and give you an idea of how all these concepts fit together in our understanding of systems engineering. Like I said, product development, to me, is the best way to learn systems engineering. If you're interested in product diffusion, start here. There's a lot of follow-up work done by researchers in product diffusion, right? So basically what it says here is that N is the total installed market base, right? How many people are currently owning the product? M is the market size. and then P and Q are factors that are specific to a product. Now, if you look at it carefully, you will see that Q multiplies by N over M, which says that Q is a function of the relative penetration of the product in the market, right? So Q actually multiplies with and is actually modifies the relative penetration of the product already in the market, which says that Q is a function of how many people already own the product. So that parameter actually controls how that affects the next person buying it. And P is independent of that, right? So P is basically more and more people will buy the product as a organically, right? So if I'm getting that correct, either way. So the whole idea is P. The thing that to understand here is that P and Q are parameters that we use, and then there are specific parameters for different products. So you can actually find tables of different product types and what the P and Q for those product types would be. And when you basically evaluate this, you get something like this, okay? Where as time period goes by, the number of new customers goes up and then down, and then the total adoption somewhat follows the S curve, okay? So now we can look at it slightly differently and look at the adoption curve in this fashion, okay? So this is number of new people purchasing the product over a period of time. You see that this has been divided into a few phases. The first phase is called the innovators. So these are people who want to buy the latest and greatest, okay? This is people who are going to buy the most expensive thing that comes out the day of. These are people who stand in lines outside stores to buy the product. And then you have early adopters, maybe not as excited about the product as others, but they're still considered early adopters. These are people who take chances. And then you have early majority, late majority, and then the laggards, right? The laggards are people who buy things after everybody's bought it, and then they're maybe waiting for a deal, or they just don't like trying new technologies, okay? So the thing to notice here, among many other things, is that, initially, even though you think that the curve is going up, the basic bulk, or the bulk of the market share happens in the middle, right? With the early majority and the late majority. And it goes without saying that the total number of people buying a product is the area under the curve up to that point, okay? So, do all products follow this model or no? What do you think happens? Especially with innovative products. Right. But this assumes that all new designs, all products are successful. It's not possible. People may try it. Let's say the innovators may try it and then say, you know what, this didn't work out, or something else came in the market that's better, or the initial reviews are bad, right? Or the manufacturer cannot scale up production, or a whole bunch of things can happen, okay? So that not every product will have the same, will continue on this curve. If you can do this entire thing, then you're successful. So not all products succeed. Okay, so we have identified a region in this curve around this point, right? When early adopters are sort of done buying the products. You would love to get to early majority and start making profits, but you can't always cross it, right? So this is called crossing the chasm. So there's a book by Moore, I think one of the editions is 2014, where they talk about crossing the chasm, basically identifying that a lot of products and new designs and new innovations don't cross this boundary, but fail at that stage. So crossing it is not just a matter of having a good product, but also having good marketing strategies and all the ability to ramp up production, ability to do a lot of things related to marketing that you wouldn't be able to do otherwise if you're not careful. Okay. So any questions here?
So actually, I have a question. So in that equation, what does capital N stands for?
That's the total installed base. So let's say N is, let's say 734,000 people have bought the product as of now, out of, let's say 2 million, which is the small m. Okay? So if I may go back. Okay, so here the capital N is the total installed market base, as in currently so many people have bought it. Okay, M is the total number. So M could be, like I said, could be 700,000, and M could be 2 million, the total number of people that you think will ever buy the product. Okay, so some people will actually work with fractions here. They would say that, forget M, let's put M as 1. Then N in that case becomes the fraction of people that have currently bought the product, right? And then the next thing multiplying is M minus NT, which is number of people that have not bought the product so far.
Sir, and P and Q also will vary according to the product.
Yes. So
what it would be for a particular product?
I don't want to. I mean, they're fractions, right? So from my understanding, from my recollection, there are numbers that you have for each product. So people have done surveys and collected data for past sales of certain types of things. For example, for a refrigerator, P could be some value and then Q could be some value. So they will say, so if you're launching a refrigerator, you can use that as a good model of that. Okay, so people have come up with tables for these things. So like I was telling earlier too, that the P and Q are factors that you associate with this. So Q is what some people will call it the factor of imitation, right? People copy others because that's multiplied by the fraction that I've already had. So people who are more interested in copying, and P is innovation, like people who would buy it just because they're interested in the product themselves. Okay. Some people also call it the word of mouth factor versus the others. Okay. So good question, right? So again, you can, yes.
Hello.
Yes, go ahead.
Sir, when the first iPhone was launched, it was a revolutionary product, and many people bought it very early. So this curve would have been skewed or something. It would have been different.
I don't know if it necessarily would be skewed. And then, of course, this is a what you call a idealized model. I mean, it's possible that it's a little skewed for every product, right? The thing to understand is that iPhone obviously is what we would call a successful product, right? So they were able to go through the entire stages of this and make a lot of money over time. And then there's also this successive launches of products of successive generations. So basically, when you're seeing that your adoption is falling, eventually almost everybody that was going to buy the iPhone in this example has bought it, then you try to launch the next generation with new and improved features, right? In fact, a lot of companies stay ahead of competition by launching a new version every year, because if you don't do it, somebody else will do it. And then suddenly, after a few generations, even though people like me I would be called I'm in the late majority most of the time with products. Okay. But after a few generations, I say, why do people buy iPhones every year? Some people I know buy iPhones every year. Some people buy it every 2 years. But even for people like me, after a few generations, I would start thinking, you know what? There has been enough innovations that maybe I should upgrade. In fact, the iPhone that I have is an SE model, and I can now already see that the pictures I take with my phone are not as good as other people's. So then you start thinking, okay, maybe it's time to upgrade. Or not, depending on if you want blurry pictures. Okay, but the whole idea is that you get the idea, right? It doesn't have to be perfectly symmetric. It's symmetric because of the underlying model that you have, right? That leads to a symmetric curve or things like that. But yeah, but the general idea is this, that there will be a slow takeoff and then early and late majority, and then sort of falling of how many people will actually buy it. And of course, a lot of things can happen. New generation products come, there's competitions and things like that. So all that complicates things. This is not easy. Of course, making a successful product is not an easy thing. But good for all of us to understand these concepts and know these concepts. Okay. And where the challenge lies. So like I said, crossing the chasm is one of the challenges of any new innovative product. So definitely recommend that book by Moore. Okay, so the next thing to talk about is concept generation. So we'll now coming back a little bit. In fact, last lecture I touched upon this in the later half, just to cover some of the topics that we didn't cover. But let's do it formally today with concept generation. Okay, so we'll do concept generation, just a general idea, and an additional example. So there's a chemical scrubber example which I go over, which is a much more complex product than just a vegetable peeler. And it's something that I have experience with because when I worked in industry, that was my project. Okay, so I was able to see it from hands-on because I built most of the thing by myself, and also try to backfill all the systems engineering principles of the concept generation needs assessment principles that I had learned academically in there. So that was a very good exercise for me. Okay, so concept generation. So we talked about this is a process of coming up with design alternatives for each component of a product or a system, right? So if you think about the functional diagram that we had, of course, it's good to have something that accepts energy and converts something into something else, or like staples a paper, or peels a vegetable, or senses if something has been accomplished, some task has been accomplished in the system. You're still not doing detailed design, like you're not necessarily talking about how you're just looking at technologies of working principles, right? Are you going to use this kind of sensor, capacitive sensor, or are you going to use some other kind of sensor? Or do you see what I'm saying? Like very general scientific principles that you would use for having that component work. Okay, and we'll see many examples, right? So we have seen some examples, and we'll continue to see examples. For example, we will ready the next staple in the stapler with the help of a spring. That's a working principle. I'm still not saying what is the spring constant of the spring. That is critical, right? If the spring constant is not high enough, then you may not be able to advance the cartridge. If it's too high, then again we could have problems, right? Then maybe there's jamming is more likely. So all these things happen. Or we will use an electric motor to create relative motion between the vegetable and the cutting edge. You could say the working principle is hand, but the working principle could be an electric motor. The working principle could be something else. So this might include coming up with novel design solutions. So if you have let's say a functional diagram and you're looking at different areas of functional diagrams, if you just go with the first idea that comes to your mind, it's not going to be a great idea, okay? And the product will not going to be innovative. You start thinking about how do I differentiate myself with the competition? You have to think about, is this novel, is this not novel, okay? I mean, I'll give you an example. I was changing the door lock in one of the doors in my house, and then I tried to do most of the things, car repairs by myself. So the thing is that I was doing that, and then there's one that you can adjust to different locations of the knob, right? But the thing is that the design that I was used to, it was pretty obvious. If you change the location of some part of the door lock or the cartridge, then it's an easy thing, it's obvious. But the one that I had, it didn't seem it was obvious. I thought maybe it's not adaptable. I can only use one distance. I cannot use the other distance. But no, I don't know. Maybe they do it differently. I looked at it. Oh, there's a little piece that once you take it off, and then you insert the knob at a different location, and it works just as fine. So this was a much simpler design than the design that I was used to. In the early design, it was obvious to me how to do it, but it cost them more money and more sophistication in the doorknob assembly to make it work. In the next one, it was not obvious, but it was trivial. It was take one part and then it works. So, I mean, you can think of it this way, like, okay, there's again trade-off, right? One company decided to do it in one way, and the other company decided to do it the other way. Now, if you think back to your functional diagrams, you'd say, you know what? That's something they did. You know what? Instead of the feature that allows you to change the location of the knob center from the edge of the door, using this way, they come up with a different way. That was their novel solution. That's what differentiated their product. And then then I started thinking about it. This is why it was cheaper. Okay, so asking industry experts, how would you do it? Like, how would you go about doing it? Asking industry experts, like, ask people, how else can I do it? How else can I do it? And then you see that people in engineering will often ask you, hey, I'm trying to look for this solution. When I worked in industry for a little bit, we would constantly discuss this. Okay, there's one way to load the spool. How about, can you think of another way where there's no backlash or something like that? So asking industry experts, people who have done it, reverse engineering already existing solutions, and that's pretty much, I would say industry standard. Everybody should do it. I said last class, make sure you, anything that you see, start disassembling and learning about how it works. You learn so much from how other people have already done it, how people making same or similar products have already done it. I mean, you think about a printer and a scanner and a copier. All of them do paper handling, right? All of them have some way of moving papers around. Some printers are prone to jamming and other printers are not. So I'm sure they're looking at those other people and saying, hey, what are they doing right and we're doing wrong? So reverse engineering and then performing literature survey, right? So people will look at trade articles, research articles, finding out what solutions exist. Now, literature survey is critical, especially for us, because you will almost never come across something that has never been done before, okay? The thing that I tell my students that if you have a good idea, assume that it was probably done 30, 40 years ago. If you have a great idea, it was probably done 15 years ago. And then one student had such a great idea that it was only done 10 years ago. One time. So that tells you that, a lot has already been done. And not just limit yourself to research articles, also look at design patents. So anybody that is launching patents is generally doing something novel, right? That's the definition of a patent. And problem decomposition helps, okay? Divide and conquer. Don't try to solve the whole thing at once, okay? You can think of many, many examples from engineering that, I want to have highly efficient aircraft wing. Okay. Well, that's a huge, tall aim. You can think of other things. Maybe I can add winglets to reduce the drag. I can maybe change the wing profile. I mean, there's many ways to approach the same problem. You can say, I'm going to focus on this, I'm going to focus on that. So if you decompose the problem, you generally have a better chance of solving it as opposed to having an overarching goal. In fact, one of the ways we can tell that somebody is really serious about solving a problem and somebody is just living in that dream world. If they have an overarching thing, I'm going to make everything better. And this person says, you know what? I really thought about this problem and I decomposed. And I say, you know what? If we could improve this subcomponent or make this more reliable, our lives would be better. Yeah, and then the last one also says the product manuals, textbooks, and occasionally patent filings prove to be very helpful. So all resources are there for concept generation. These will just give you ideas. Okay. Now, one thing you might have heard of is brainstorming, right? It's a common technique used for concept generation. We did a little bit of this in the class last time with the vegetable peeler. But yeah, it's a commonly used technique. Brainstorming is
n number of people coming together and discussing upon the ideas they have for a particular topic.
Right.
And coming together on a single, getting into a consensus.
Right. So again, exactly, right? So it's basically, you say that if multiple people are working in a team, they're more likely to come with a design. And then, we've been doing a lot of work on this these days through agent-based models that, there's a lot of things that happen in brainstorming sessions that we should think about. But yeah, that's the general idea. So we'll get to that in a slide or two. So it's a way to come up with creative ideas of new designs or improvements by using inputs from multiple individuals, right? Not just one, multiple individuals. So you assemble a team, obviously people who you think are capable of finding solutions to the problem. And then you give them a design problem. Now, they will propose, discuss, and evolve new ideas through constructive interaction, right? So people will come up with new ideas, propose. Not everybody is allowed to propose, let's say, in an ideal session, discuss, evolve, and then come up with a solution, right? So oftentimes you will see this person has a solution that doesn't make sense, and that person has a solution that doesn't really make sense, but together combined, or they give you new directions that you can pursue. So designs and ideas evolve during the course of a discussion. Right. Now, typically you do this after customer needs are identified. If you have to know what the customer wants. And a functional diagram is available, is something that, I recommend, because you can, anytime you can have a little bit more clarity as to what the product is trying to do, and what are the different components of the product, then life would be better, right? So you can say, okay, well, you know what, we'll use a generic this, generic that, generic that. For this, I can use a new solution. And that's how we used to do design. And we have done design in the past, where most people will say, you know what, for this sensor, we can just buy this model made by Siemens, and for that, we can just use this metal. There's an already existing solution for this. There's off-the-shelf sensors for this. There's this for that, and we can order this from outside. This we can do at home because we think that in-house, because we think we can do a better job or do it cheaper. Okay, so. Okay, so any disadvantages or challenges with brainstorming? You may get off track. Why would you get off track?
So, different people might have different ideologies, and it might trigger I say one point, the other person will say the second point, and they might differ from both the points might be contradictory to each other, but they might think that both the points might contribute to the main problem or the topic of discussion that they are into.
Both of them are correct, right? So you can go off track. People may not always appreciate each other's comments. What else can go wrong? A lot can go wrong, right? A lot can go wrong when there's a lot of people involved. So, and then this has been studied from a lot of different perspectives. So we have looked at it through agent-based models. So basically, we do a simulation of people working in a team and then see what happens when you have people with certain cognitive profiles working together, right? So if you have somebody who's vocal, okay, they may be more confident, they're more vocal, they overtake the conversation. Now, this is okay if they also have strong technical skills. But oftentimes we see people with strong technical skills are not very vocal, and then they're also quiet. So now the problem is that if the team is not composed properly, people can monopolize a discussion even though they don't quite understand the solution. The person who has the solution doesn't have the confidence to speak or doesn't have the wherewithal to fight their viewpoint or fight for their viewpoint in face of opposition. So there's a lot of these kinds of things that can happen. There's also this idea of creativity that is sometimes looked at, that people have there's novel solutions. Some people are good at coming up with novel solutions. And some people are good at coming up with systematically solutions, right? So if I use, let's say, some finite element code, and then they're systematically coming up with different design solutions, other people will say, how about we try something like this? And then it's not, they didn't approach that solution technically. They come up with it more intuitively, right? So all those things become important. I mean, there's a common example that's given of a car with square wheels. I don't know if you've heard about that, right? So if somebody proposes, actually we'll get to that in a second. So group dynamics play an important part, right? Group dynamics, how people work with each other. Some people may have preferences for each other. That's another thing that, I like this person, so I'll let them speak, or I'll support their viewpoint, even though they may or may not be correct, right? Some people have biases, right? I don't like people from a certain region. I don't like this gender, and those kinds of things can also affect, or I should say, people don't prefer certain genders. So there's all these things that biases get into our discussion. So brainstorming can get off track. Right? Fixation is another thing. So this is not necessarily related with people's personalities. It could be like, if somebody proposes an idea, then you get fixated to it. Like, that's a good idea. And then you start thinking about how we can make that idea work, as opposed to maybe it's not such a great idea, right? So you get fixated on a solution, and then you find more and more different ways of improving it. It's also called anchoring sometimes. So again, the suggestion is that you should have brainstorming sessions done over multiple sessions. And then we were finding that it's important to also let people think on their own. So you have brainstorming sessions, and then you let people work independently and try to work on the solution themselves. So if you have individual investigation followed by team meetings, individual investigation followed by team meetings, then usually things go better. Okay? And then quick rejection of novel ideas. So just because something prima facie doesn't sound like a good idea doesn't mean that it cannot be evolved into a good idea, right? So that's the evolution side of things that I was talking about. Many times you'll have an idea that doesn't work well by itself, but unless somebody finds a solution to that also, right? So the earlier example I was trying to give you was that a car with square wheels, is that a good idea? What will happen?
So, because in square wheels, friction will be more. Like the edges will be there. Square will have the edges, and that edges will make the wheels to, it's prone to more accidents. I think so. It will not move.
Well, it might move, but then the car will jump up and down 4 times every revolution, right?
Yes.
Because the distance from the center is different at different points. But that's a terrible idea. But then you could say, you know what? I know that a square wheel car will have predictable motions, right? That every 4 times at 90 degrees separation, 4 times the car will actually jump up. Then I can do active suspension to cancel that. Then you say, you know what? Forget the square wheels. Now we have an idea. We should have active suspension. And then you drop the original idea of square wheels, but then you say active suspension can be used in other settings also, right? So you can have, and some cars have active suspension. So square wheels itself seems like a bad idea, but it can lead to you thinking about something else, which may become a good idea, right? And that's the whole concept here, right? So quick rejection of bad ideas leads to this. And we will talk, there's many ways to look at this. So when even in optimization, we say convex optimization versus non-convex optimization, local minima versus global minima. So local minima are you're so stuck in that area that, you cannot get out of it. So a lot of heuristics like genetic algorithms or simulated annealing will allow you to come up with the worst solutions, because maybe a good solution lies next to a worse solution. So you're able to pull yourself out of the local minimum. Okay. Can you think of an idea or a situation where a bad idea became a good idea? Anything you can remember from your discussions? or sometimes like just because we allowed new discussions to be had and new concepts to be considered, we came up with a novel solution. It's all over the place, right? So the fact that we're able to do things, now we can recover parts of rockets, right? Well, this has been around for some time. I mean, people are talking about the 40, 50 years ago that, if we could recover, and then it looks like the technology had existed until we actually recently started doing it. And then we can do it now. So,
Sir, actually, I want to give an example. Sir, before iPhone, there was BlackBerry and physical keyboards. So when iPhone first introduced digital keyboards, then it was a bad idea at the time. But over time, it became a good idea. Everybody got used to it, and it also has many conveniences.
Okay, why was it a bad idea initially?
So because people were used to physical keyboards on like BlackBerry mobiles.
Yeah, so it was a bigger challenge for them to get over that, that comfort level with physical keys. And then prior to that, if you remember, touchscreens didn't used to be that accurate. So a lot of engineering went into being able to sense and predict what you're trying to type, right? So now they actually do predictive typing. So they can predict the words you're going to say so that letter that it thinks that you're most likely to press next, the sensitivity area for that letter increases. Right, so you less like sometimes I'm sure you've noticed that when you're typing, you're like, I don't think I really said W, but how I was at E in a QWERTY keyboard and I still read it as W because it knew that most common words, the next letter would be W. So there's engineering that happened to make that into a good idea, right? If you look at old resistive screens, they're not as accurate. And then all sorts of bad things happen when you don't have good touch screens. Okay, so
businesses might start off as a very bad idea to start some business, but eventually there could be some flip sides and good alternatives.
Right. So the point that you made was, I'm doing it for the recording, that even business ideas may be bad or sound bad initially, but then they end up being good.
Initially they thought, and I'm not sure if you watched it, but initially they thought that may not be a good idea for cricket because they reduce the number of overs. But then eventually the benefit was that grassroots levels, there are a lot of great cricketers that come out of it.
Right. So local sports franchises and all that helped in the long run. Beanie Babies is another example that people could not explain how Beanie Babies became $1 billion because toy industry, but it is. So the whole idea of how to work well in a team, again, is a well-traveled area. There's a whole bunch of literature on this, whole bunch of best practices, how to assemble a team, how to give them design problems, how to do team dynamics, how to manage the discussion, and so on and so forth. But even then, there's alternatives to brainstorming, right? That independent investigation is a big one. Like, okay, if the team discussion is not working, then you let people investigate themselves and then convene and discuss the discussion. And then you have, researching implementation of similar products. Like I said, okay, well, brainstorming did not give us an idea, but I can look at similar products, the ones that I'm making, see if I can get any ideas. So if I look at a copy machine, I can use that to design a printer. And there's other things like, you're using stimuli related to the product or using stimuli unrelated to the product, right? So sometimes we can think about similar applications and say, okay, this is how they're doing it. Maybe that's a good idea here too. Or you can look at something completely dissimilar. There's, again, many examples of this when people looked at one design in the unrelated area and that gave them an idea for what they needed here. Okay, and then redrawing the functional diagram. So again, coming back to what you were saying, that's why I mentioned to you last time that this comes back many times in our discussions, that functional diagrams are not set in stone. You can add more to see how you're going to how you can accomplish a certain task. One component can be broken down into multiple components, and then you can say, you know what, this is how we can do it. And one thing that always used to surprise me is certain car lots or car parking structures used to tell you how many spots are left. And the naive engineer at that time, me, used to think, how do they know how many car spots are left? I mean, in a parking structure, there could be 1,500 parking spots, right? How do they count in real time? Because people can park anywhere they want. Well, any parking spot they want. How do they know in real time how many parking spots they have left? Yes. So one really complicated way would be, but the more accurate way would be that you can put a sensor in each parking spot, and you can count how many are occupied, right? That's a more complex way of doing it, but then it's a more accurate way of doing it. What can go, and the other solution, like you suggested, is you just count the number of cars that go in, count the number of cars that come out, and you're done. What can go wrong there? No, let's say there's only one gate.
So if the calculations go wrong, like if the sensor is fitted in every parking, and if the sensor itself is not working, then the calculation might go on a toss. And if for example, one car is coming to park and the parking is filled, it may have to look for another parking which may not be available.
Right, but we're talking about the other idea where we just measure or count the number of cars that go in or out, right? And then we subtract and add based on that. No, so the issue with that simpler, cheaper idea is that, people can walk by and they may trigger the sensor, or a car may be picked up twice. Sometimes a car may not be picked up because of reflections in the sensor or something like that. Then the problem with that second, cheaper, more robust, I shouldn't say robust, simpler approach is that you can have cumulative errors, right? Once you start having counting errors, now your whole calculation is off. And guess what? Sometimes I would see that, like, oh, hang on a second, that doesn't make any sense. So either way, there's different ways to do the same thing. It comes with pros and cons. So we'll go over some brainstormed concepts. So I try to talk about these examples because these are, one of them was the brainstormed concept examples for a peeler, right? So here we're looking at the function of vegetable goes in. Everybody can draw a functional diagram, right? Basically, just make sure that you separate the flows. We have information flows, we have energy flows, and we have material flows. Those are the main types of flows that we think about generally. And then if you have different types of sensor flows, you can do that as well. So you have vegetable and energy going in. Somehow you have a way of holding and orienting the vegetable. And then the energy is used to remove a layer of skin from the vegetable. And then some way of examining whether it's done or not, right? So obviously you don't want to just do something and then have an open loop system where the solution was not found and you quit. So then you have a loop. Every time you notice that some part is left, you reorient it, and then you peel the vegetable, and then you go from there, right? So that is one way you can draw the functional diagram. The thing to notice here is that, and like I said earlier, you will focus on one of these, right? And then you will say, okay, let's try to find a solution for this. And then in the end, we'll try to put it together. Hi. Okay, so what I did is that I took it out from here, and then I looked at what are the inputs going into that block, what are the outputs, and what can I do with it, and what solution I can find with it, right? So if I take it out, I can quickly identify, well, it has to have some energy going in, right? Examine whether fully peeled or not. You cannot examine, you cannot do any sensing and decision making without energy. Then you have the vegetable, the physical vegetable going in, and then seeing whether it's fully peeled, and then somehow outputting yes or no. Okay, so no for a human being is just no. Let's do it again. For an automated system, it might be something else. Okay, the other advantage is that we identify important functions that need to be performed. For example, and I think I made this point last class too, that you may not think in a functional diagram, if you separate things, you say, well, hang on a second, I need an entity that does this, right? So if you want something to tell us whether it's fully peeled or not, we don't think about this, but we have to if you want to automate this process. We could also just do a mechanical switch, okay? Thing rotates, it hits the switch, turns it off. Okay, so in electromechanical systems, limit switches are all over the place. So that's an indirect way of doing it. Now, somebody could, let's see what I have here. So again, this is something that I've discussed in class with students, like, some concept examples of examining whether a vegetable is fully peeled. Some students suggested visual inspection. So it's automated, but I can do, well, for non-automated, you do visual inspection anyway. But you can just stand here, and then you can have a button and say, no, it's not fully peeled, turn it over, and the machine peels it. It may be useful in certain cases, but I can't think of many. A camera system with processing capabilities. So these days we can do machine learning, and we can actually do it live, right? I mean, it's becoming so easy now. There's libraries available on Python, and you can actually design it'll be a class project these days. Nothing more than that. So basically, a camera takes a picture, determines whether it's peeled or not. Maybe you can take multiple pictures from different angles and say, you know what, go cut here, and then you're done. Or the limit switch idea that I showed last time, but it could be wasteful as well. Okay? So I'll quickly go over the next example. Yes? Uh-huh. So the point that is being made is that if we start installing camera systems in vegetable peelers, it'll be very expensive, right? But then you can think of capital cost versus recurring cost, right? So capital cost may be high, but if you have a restaurant and then you peel, 800 potatoes in a day, then it's not a bad deal, because then now you can actually get rid of a whole person. You're not paying their salaries. So depending on what the throughput is, right?
Also in the diagram, the peel itself is also an output. So in the functional diagram, the inputs are energy and the vegetable, and the output is fully vegetable. But actually the peel is also an output. It should come out of the system.
Right. So it should come out of the system. That's a good point that you're making. Again, we always say the context, right? If you're thinking about it, then yes, you could say, you know what, I need a way of collecting the peels so that I can discard it or do something else with it. Maybe I can
put it into a juicer. So there is.
Put it in where?
Into a juicer.
Juicer.
Yeah, you can put. So again, great idea. So so we're brainstorming without even realizing it. Okay. The idea is that, or the suggestion that was made is that this functional diagram can be modified. Great. That is always the case. Okay. We can add a feature. Okay. We can collect the vegetable peels and do something with it. So one suggestion could be juicer. Like, some vegetable skins have a lot of nutrients, so you can recover them. Great. Other people would say, you know what, just throw it away. So you still need a way of handling all that. So coming back with your idea, this is what I was talking about, idea evolution. You said earlier it could be expensive, right? That's a valid point. But if you have huge throughput, then it's no longer expensive. Well, she said, what to do with vegetable peels? I said high throughput vegetable peels means a lot of waste. Somebody needs to carry it away. Even if we don't think of using it for any other purpose, we now have to think about getting rid of it. Another thing people do is composting, right? So they basically put it in the dirt, and the thing is organic, bacteria and everything decomposes it. Now you have really fertile soil. So people use that for that as well. Like, you can put vegetable peels in your plant bed, flower beds, or even in your flower pots, and then you generally get much more nutrients out of it. So there's many ways to use it. Some restaurants I've seen in the US will actually systematically give it away to people who would use it for growing more vegetables, like coffee grounds are useful for certain things, and so on and so forth. So yeah, great idea. And you can always, and all ideas will come. So hopefully I'll try to add it next time I teach this class, that, okay, somebody suggested we should do something with peels. Yeah, animal feed is another example. So yeah, and then that also actually could also change your cost dynamics, right? So you could make money that way, or you can create a social image that this company is more environmentally friendly. And of course, a lot of companies will advertise like, we take care of, we don't create garbage. We actually help the environment by creating vegetable feed. Some companies, some manufacturing companies, actually their entire profit is selling metal scrap, metal shavings, metal scrap. So they'll do processing, and in I think we're talking about target costing versus cost plus methods. Some larger companies, they are so aggressive with pricing with their suppliers that you would see that the suppliers don't make any money selling the product or the component to the OEM or the whoever they're selling the product to. Their entire, so they make this, however much it costs them, that's how much they get from the company. It's zero. But they have all this metal waste that they sell, just like the peels, and then they make a lot of money from that. So all this has financial implications too. And these are exactly the kind of things that, I'm glad that you're taking this class. That I don't think of any other class where these things get discussed like this. So I think this is a pretty cool thing. You think of products and entrepreneurship and how to make new products, what to think about selling products and recovering value and so on and so forth. Yes, thank you. Apologize for the small slides. I'm used to bigger screens, so either way. So what we do is that we isolate one of the blocks in the functional diagram, and then we try to come up with solutions for that, right? So when I used to do a stapler, I said energy could be coming from somewhere, right? From your hand. Let's say when you staple something, you provide energy. Some students said, why don't we have an energy storage here? What if we want to store that energy? Well, that's a good idea. So I put a block of energy storage in here. Okay. Now, we all know that energy can be provided by hand, electricity. So you plug it in, and then there's an electromagnet that staples the papers. You can have a battery and an electric motor. So, and you can have a chemical charge also, somebody suggested. But the whole idea was that if you're thinking of storing energy, then maybe you don't have to connect it to the mains. You can have it anywhere. It's handheld, but it has a little battery that stores the energy when you. So of course we have staples like that. I've used them, and then once there's a chemical charge, maybe if you need so much force to staple something, you could have a tiny explosion. Well, we can think of scenarios where that would make sense.
So,
yeah.
Yesterday, as ma'am told, in the case of stapler, what will be the functional requirement for safety? Couldn't be like that in the stapler, like the side we hold our hand, couldn't be made up of rubber for a safety purpose? Like if it falls on the leg won't hurt.
Yeah, so making like making it more ergonomic. You're saying, yes. right? So yeah, all those things could be there. So those could be distinguishing factors in there. I mean, I think that that's something you would do in the final form of the product, right? You can add. So I guess the lesson here is that engineering design is iterative. Okay, you never come up with the best design in the first go. Here, you're trying to find solutions to the novelty of your product, right? You could say that I designed the stapler just like anybody else does, and then I'll make it ergonomic by adding, protective sheathing or something like that. That's one way to think about it. So it's iterative. You keep improving the product over time until it gets better and has all these features that you want. So initially, this is something we have to be, I talked about square wheels earlier. We have to consider all ideas until they're found infeasible because of one reason or the other, either too expensive or unsafe, right? So if you start talking about chemical charge, well, yeah, too unsafe, right? But of course, similar ideas exist when you have, a pneumatic stapler. A pneumatic stapler uses not chemical charge, but uses high pressure gas to work. So, and then you will need to combine these together, right? So if you have, let's say you're saying, I'm going to use an electric powered stapler. Okay. I had a friend who was an ex-Navy guy, and he had a way of stapling that he could staple any number of pages that the stapler would hold, and somehow he was able to without bending the staples. So I learned that technique from him. It was awesome, right? But you could also say that some of those human hand variations can be avoided if we use an automated stapler. So if you have an automated stapler that is electrically powered and so on and so forth, but you now have to think about okay, well, if it's electrically powered, then you need provisions for providing wiring and things like that, way to activate, deactivate the motor. And then now you have geometric constraints, right? So you cannot make it super tiny. Some staplers I've seen are really small because but if you start adding electromagnets and wiring and switches and things, it's not going to be a small stapler anyway. And then hand-powered staplers will need to be ergonomic, to the point that was made earlier, that if it's ergonomic, it's easy application of force too, right? And if concepts conflict, the combination could be discarded or modified. This doesn't work with that. Okay, so modify this, modify that, or come up with a new design. So, yeah, so energy storage was one. We already talked about different ways of stapling. Large copiers, right? Copying machines can staple papers now, right? You've seen that they do a tremendous job. When I'm giving an exam, I can put 10 pages and I say, okay, make 100 copies and collate and staple top left corner of every single one. Okay? And it staples top left corner, but it does not. Imagine a thing like that getting stuck or tangled. That would be bad, but it doesn't do it. So of course, these things have been perfected over time. People have thought about how to improve these designs so that we can do continuous stapling without worrying about it. And then again, the thing with that you get out of more expensive things, to the point that you're making more expensive things that reduce variability, is that you can have repeatability now. You can do over and over again. So a vegetable peeler with all those camera systems can do it over and over again with the same consistency. Humans can get tired, humans can make errors, humans can get hurt and things like that. So you avoid those kinds of things. Similar things with staplers.